Hello and welcome to a new episode dedicated to the routing scale of the NCS 5500 routers, the infamous FIB size. And more specifically today, we'll cover the systems based on Jericho 2. Today we'll talk about scale, on-chip or with external eTCAM, how it handles a full internet view, and how fast we program entries in these memories. All of this just after the intro. My name is Nicolas Février and I'm TME in the MIGBU, what used to be the Service Provider Business Unit in Cisco. I covered this aspect in multiple articles and videos in the past. Understanding how to optimize the prefix allocation to specific internal memories was key to support a full internet view in Jericho and Jericho Plus, particularly when used without external eTCAM. By the way, it's very important to point to this article too, on the decommissioning of the Internet Optimized mode. If you have this feature configured, you need to pay particular attention to this topic, because we decided to remove it in phases, first in iOS XR 7.3.1, and the second part for IPv6 in iOS XR 7.4.1. Okay, but today we will talk about Jericho 2 in the NCS 5500, or what we call the NCS 5700 for the fixed platforms, and how this chipset stores routes in hardware. As you know, we sort the systems in two big categories. Those without external eTCAM, that means relying only on on-chip databases, and those with external eTCAM, identified by the product name via the two letters SE. For example, we have the line cards NC5724DD without external eTCAM, NC5718DD SE with external eTCAM, or with the fixed systems NCS57B1 6D24, no eTCAM, NCS57B1 5DSC with external eTCAM. Let's take the first case, no external eTCAM. On these systems with the prefixes and multicast routes are stored in what we call the LPM, while the MPLS and bridge domain MAC addresses are written in another database named LEM. On the SE systems, all v4 and v6 prefixes are going to the eTCAM, and that's also where we have the access list entries. In LPM will go the multicast groups, while MPLS and MAC addresses will be stored in LEM. In the next software releases, we'll come up with different MDB profiles, MDB for modular database, that will carve the different memories to specialize the router in specific role, more L2 or more L3 for example. So the size of this LEM or LPM will vary, but still the logic described earlier to store the routing information will stay the same. Okay, let's take a look at all the resources used for a full internet view. We are running iOS XR 7.3.1 in this chassis, and we have Jericho Plus with OP eTCAM in slot 0. I will call it J plus SC from now on. We have Jericho 2 with OP2 eTCAM in slot 3. I will call it J2 SC. And we have Jericho 2 without eTCAM in slot 7. I received a full BGP feed of almost 837,000 IPv4 routes and 121,000 IPv6 prefixes. We stream all these counters through model-driven telemetry and display the gauges in Grafana. In slot 0, J plus SE, logically all the routes are going to eTCAM, v4 and v6. Same for slot number 3, with J2 SC, all v4 and v6 are stored in eTCAM. Finally, in slot 7, we have J2 line cards without external eTCAM, so the v4 and v6 routes are going into the LPM. One gauge here is used for v4, the other one is used to represent v6. Nothing goes to LEM. But you can see here we have actually a display bug, and I'm putting some more details on it in the xrdocs article coming with this video. But all the routes are actually programmed in LPM. Let's take a look at the CLI now. With the show controller command, we can check the J2 SC line card in slot number 3. The card is qualified today for 5 million routes. So internet is just representing 17% of the resource. and not more than 6% of the v6 capacity. Just for your information, I checked the routes in Jericho Plus card here in slot 0, and I confirmed that all the prefixes are going to eTCAM. Still plenty of room on this card too, as you can see. Now, let's check the J2 non-SC in slot 7. We verify that all routes are indeed going to the LPM, and we are not using more than 37% of the capacity. Nothing goes to LEM. Exactly what we displayed on the Grafana, of course. Since I like to play with these things, I reused the projection model created a few months ago, where I predicted the internet size evolution. Something linear for IPv4, with the disaggregation of the /24 prefixes, and something more logarithmic with the IPv6/48 progression. I invite you to take a look at my very approximative methodology in the article below. So we advertised the additional routes up to 2028, both for v4 and v6, and that represent 462K additional v4 plus 239K extra v6 prefixes. On the data visualization tool, we see these routes are all programmed in eTCAM for slot 0 and 3, and in LPM for slot 7, as expected of course. That's almost 1.3 million v4 and 360,000 v6 routes. Back to the console, we check the prefixes length distribution with show DPA resource CLI. For IPv4, the largest population are the /24 and /22s, while with IPv6, it's mostly /48s and the additional route I created in /64. Still with the CLI, I check the resource utilization of the LPM. That's a total of 63%. And to be complete, I verify on J plus SC, 32% v4 and 18% of v6. And on J2 SC, we are at 26% of v4 and again 18% of v6. Tons and tons of space. That's a lot of margin to grow, or potentially used to something else. Back on the graphical view, I'm showing here the routes per resource. That includes also the RIB, the LEM, LPM, eTCAM, etc. On the second graph, I'm showing the programming speed inside these specific memories. It's something we tested already in this video above for J plus eTCAM, so we'll only run the test for J2 in this second part. We'll check how fast we can program entries in LPM and in external TCAM of a J2 system. In terms of methodology, you have to understand a few things. First, it's mandatory to shut down all line cards except the one we are testing. Also, we are checking the maximum programming speed. That means we need to push the route as fast as possible and avoid creating a bottleneck in a chain, for instance, at the route processor level. So we are using an internal tool to rapidly announce through BGP a large block of routes. In this first example, I'm starting with 1 million IPv4 prefixes. The first graph is showing the number of entries for the RIB table in red and for LPM in orange. And we'll test both the programming and flushing, the withdrawal speed of the routes here. So I start the advertisement and I stop it a few seconds later. You can see on this graph on the top that RIB is receiving the route and the LPM is being programmed at a slower speed, which is totally expected of course. At that point, the routes are all programmed in LPM and we reached a plateau of 1 million entries. Now we stop the advertisement, the routes are quickly removed from RIB and more slowly from LPM. The second graph is representing in prefixes per second the programming speed for LPM. It fluctuates between 26 and 29,000 routes per second. In the second block, we see how fast we flush the routes out of this LPM, and here again, in the same range, from 27 to 29K per second. And we repeat the operation with 1 million IPv6 routes, advertised again with our internal tool. Once all the routes are received, we wait a few seconds and we stop the advertisement. The routes are progressively deleted from LPM. Okay, let's take a look at the graphical representation of this test, and I jump directly to the prefix per second graph. The routes are programmed at around 30 to 32K per second here, and deleted at a speed fluctuating between 27 and 30K per second. Okay, let's move on and quickly repeat the test with the second line card, equipped with the Jericho 2 and external TCAM. Okay, I'm shutting down the first card, I restart the J2SC, and I'm gonna relaunch the test. IPv4 first. You understand the methodology now, so let's jump directly to the IP route prefix per second graph. Programming is done at a speed between 31 and 32K prefix per second, and flushing speed is between 31 and 35K prefixes per second. So it's all more or less in the same range. Quickly, I'm showing also the other graph with both FIB and eTCAM, and no surprise here, it's really behaving as expected. And I'll put more details on the companion article with more details like the FIB convergence speed. For the IPv6, we repeat the same test methodology one last time with an advertisement, a pause, and a withdrawal of the routes. They got programmed in hardware at a speed varying from 25 to 28K prefixes per second, and for the flushing it fluctuates between 24 and 27K, more or less. And that's it. I hope this test answered some of your questions related to the routing programming in J2-based systems, where the prefixes are stored and how fast it's done. Let us know in the comment below if you have other test requests in mind. Thanks for watching and see you in the next one. The NCS 5500 engineering team is already preparing the next generation line cards based on Jericho 2 forwarding ASICs. These line cards will offer 9.6 terabit per second per slots. We will have 2 Jericho 2 on the board, each handling 12 ports 400G Ethernet. We will also introduce new generation fabric cards. For an 8-slot chassis, each fabric module is powered by 2 Ramon ASICs. Each pair of Jericho 2 and Ramon is interconnected via 9 SerDes links at 53.1 GiG. Let's take a quick look at the systems running in the lab. In slot 3, we have the 24-port QSFP-DD line cards. All ports are connected, and we can see the status and protocol are up and up. We are using 400G QSFP-DD passive copper cable in most of the ports, and for the particular case of port 11, we're using a passive lookback. We'll explain why in a minute. With this shell command, we verify the SerDes speed is indeed 53.1 gigabit per second. This demo is using an MPLS snake test. The traffic generator is connected to line card port 0. All traffic flows are going from NPU 0 to NPU 1 and vice versa through the fabric. That means no local routing or forwarding is done on the ASIC. All the ports are looped physically with the PCC, with the exception of port 11, which will use a passive loopback to interconnect RX and TX. And the traffic is flowing back, hop by hop, to the traffic generator. With this approach, we can load the 24 ports with line rate traffic, that's 9.6 tera, bidirectional. On the traffic generator interface, we verify we have indeed 400 GiG flowing and 0 packet loss. Traffic has been running for 1 hour and 44 minutes already without a glitch. The rest of the counters will show the traffic at layer 3 with the header overhead. On the router console, we verify the interface statistics. They are displayed at layer 3 too, and verify the line rate traffic on all 24 ports RX and TX. The line card is up for more than 7 hours, and we didn't lose a single packet. The NCS 5500 Jericho 2 program is making very good progress. Today, we are able to demonstrate IP or MPLS traffic forwarding at line rate through the 9.6 terabits per second line card and the next generation fabric. Thanks for your attention.